Okay, so what we're going to be starting to work on in this section is we're going to start looking at different techniques for integration. Techniques for integration are actually really important because what they do is they allow us to expand our understanding of how integration works and some of the different ways that, so the different and interesting ways that mathematicians have gone about actually doing integration and then solving more abstract or complicated proofs and things like that using some of these techniques. All right. Um, in addition to that, what it'll do is it'll help us to understand things like differential equations later on, or some of the different applications that you might get when you start doing some physics or statics or thermodynamics, things like that. Because a lot of these integration techniques are used there, all right, because they've got very difficult functions to integrate. And so consequently, they'll use these techniques, and you want to know how to use these techniques too. So let's take a look at integration by parts. And what we're going to do is we're going to get the very basic theory. It should only take us a minute or two because it turns out it's just calculational in many ways as to how we end up with this theory of the integration by parts. So let's suppose that we have a function. And we have this function and it's h of x equals, and it's a product of two functions, g of x times f of x. Okay, so we've got h of x equals g of x times f of x. And let's say, for example, that what we want to do is we want to go out and we actually want to take the derivative of both sides. Okay, so we end up with h prime of x is going to equal, and by the product rule, it's going to give me g prime of x times f of x minus f prime of x, or excuse me, plus, sorry, f prime of x times g of x. Okay, and that is, so that's, that's the derivative. And then let's say now that what we want to do, for the sake of fun, we take an integral of both sides. So we're going to get h prime of x dx will end up equaling the integral of g prime of x f of x times f of x plus f prime of x times g of x all dx. All right, seems a little backwards, but well, we'll get there in a second as to why we did it. And so we can then separate out the the right hand side and make it into the integral of g prime of x f of x dx, okay, plus the integral of f prime of x g of x dx. This is now going to equal h of x, which is just going to equal f of x g of x. And the reason why it's equal to h of x is because we took the integral of h prime of x. Makes sense, right? By the fundamental theorem of calculus, you take the integral of something that you took the derivative of, you're going to get back to the original function. Now what we're going to do is we're actually going to go in and we're going to solve for f of x g prime of x dx. So the integral of f of x g prime of x dx is then just going to equal, it'll be this, f of x gx minus the integral of f prime of x times g of x dx. And that's going to be the basis of the integration by parts. Okay, what we'll do is we'll let u equal f of x. Okay, we'll let v equal g of x. So du is going to equal f prime of x dx, and dv is then going to equal g prime of x dx. When we substitute back in, what we're going to get is we're going to get the integral of f of x g prime of x dx will equal the integral of u dv, which will equal, and then this is going to be, for us, this is going to be the big part where we're going to use this for integration by parts. It's going to be u times v minus the integral of v du. Okay, and just take a second, pause the video right now, and see how it is that we ended up with that substitution. Okay, this here, that is the equation for the integration by parts. Now the theory doesn't really make that much of a difference. What really is going to make a difference in this case is how we utilize that function or that equation for the integration by parts. So let's take an example. Let's integrate, okay? We'll take the integral of x sine x dx. So this, we can't use a u substitution here. This is not one of our standard or basic integrals. So what we're going to do is we're going to utilize that function. We're going to take that integral of u dv is equal to uv minus the integral of v du. Okay. Now in integration by parts, one of the skills that we'll develop, all right, one of the techniques that you're going to well, actually one of the feels that you'll get for doing this kind of mathematics is which one is going to be u and which one's going to be du. Okay. Excuse me, which one's going to be u and which one's going to be dv, right? Because we've got u dv right here, and we've got to choose one of our functions, all right, to be our u value and the other one to be the dv value. Okay. So what I'm going to start out with is I'm going to say, okay, in general, we're going to start with any power of x, right? Any kind of like polynomial or power of x, they're going to make that u. So we're going to let u equal x. And so then dv, okay, in this function, that dv is going to end up being sine x dx. All right, so you've got, there's the u, there's the dv. Now, if you remember, what we're going to do now is we're actually going to need to find both du and also v. So that means that we're going to take the derivative, okay? So du is going to equal d dx of x, okay? So du is just going to equal dx. That's the derivative of x. That's it, right? It's 1 dx. Done. Then what we're going to need to do is, in order to find v, right, v is going to equal the integral of sine x dx. So v will end up equaling negative cosine x, and that's it. Okay? So we now have, taking from u, we get du, and taking from dv, we're going to get v, and now all we got to do is plug them back into our equation. So we end up with x times negative cosine x minus the integral of negative cosine x dx. Well, that's great news, right? Because all we have to do now is just pull out that negative from cosine x dx, and I can totally integrate cosine x dx. So now I end up with x cosine negative x cosine x plus the integral of cosine x, which is going to equal negative x cosine x plus sine x plus c. And that is the integral of x sine x. So what we did was we selected one of our functions to be the u and the other function to be the dv. Okay, we took the derivative of u, okay, in order to find du. We took the integral of dv to find v, and then we plugged it back into the function or the equation there to do the integration by parts. Let's take a look at another example. This example now is going to be, let's integrate the integral of x squared e to the 3x dx. Now in this case, what we've got is we'll let u be that power function. We're going to let u equal x squared, and we're going to let dv equal e to the 3x dx. So du is going to then equal, we'll take the derivative, it's going to be 2x dx, okay? And v will equal 1/3 e to the 3x dx. All right, so we just took the integral of dv to get v, and we took the derivative of u to get du. Now I'm just going to plug it back in, right? So remember, my formula is uv minus the integral of v du. So that's going to be x squared times 1/3 e to the 3x minus the integral of 2x times 1/3 e to the 3x. Well, now if I actually simplify this, all right, I end up with 1/3 x squared e to the 3x minus 2 times the integral x e, or 2/3, excuse me, e x e to the 3x. So what I end up with is 1/3 x squared e to the 3x minus 2/3 x e to the 3x. Well, now what I have is I have another integral that I'm going to have to use integration by parts with. I'm not actually going to be able to integrate this with anything else that I already have right now. So I'm going to have to use integration by parts again. So what I'm going to do is I'm going to kind of keep this guy over to the side. So that's 1/3 x squared e to the 3x. And then I'm going to again use integration by parts here. I'm going to let u equal x, okay? I'm going to let du then equal dx, because that's the derivative of x. And then dv will equal e to the 3x, and so v will equal 1/3 e to the 3x. Pardon me, the dv should have a dx on the end of it too. Okay? So what I now have is I have minus 2/3 times the quantity, because now I've done integration by parts with this entire thing, minus 2/3, and it's uv, so it'll be 1/3 x e to the 3x, right, uv, and then minus v to u, so that's going to be minus 1/3 e to the 3x dx. With that finished, what I can see now is now I can actually go through and integrate this. So this is going to end up equaling 1/3 x squared e to the 3x minus 2/3 times 1/3 x e to the 3x minus 1/3 times 1/3 e to the 3x plus c. And so now what I'm going to do, one of the things that you're going to notice here about what I did here, and it's just generally a good idea. I end up, if I simplify as I go along, I end up with making more mistakes than I'd like to. So basically, I utilize parentheses and brackets in order to help me kind of keep all of my my coefficients together. Actually, is one of the biggest issues here. So you'll notice that that's what I did, and then at the end, I'm going to do all of my multiplication. So this is going to give me 1/3 x squared e to the 3x minus 2/9 x e to the 3x. And then this is a negative 2/3. Okay, so negative 2/3 times negative 1/3. So that's negative times negative 1/3, which is positive 2/9 times 1/3 is going to be plus 2 over 27 e to the 3x plus c. All right, now one of the things that I want to demonstrate here, it's basically what we did was we used integration by parts multiple times in order to solve or find this integral. Okay. The thing about it is that you've got to be actually very cautious and very detail oriented as you do your integration by parts. In addition to that, I want you to notice that you can use integration by parts as many times as you need to in order to go in and solve the integral. What we're basically doing here is we used it once and then we ended up with another integral that required integration by parts. So in order to find the complete integral, we had to do integration by parts multiple times, and that's totally allowed, and it's totally something that's expected. What I'm going to do in this next one is I'm actually going to show you a kind of a shortcut method, or a method to keeping these things organized when we have a very special class of functions that we're looking to integrate. Let's say, for example, that now we want to take a look at integrating some special functions like x squared e to the 3x dx or x to the 4th sine x dx. And what we're going to use is a special thing called the tabular method. This is basically, it's not really a shortcut. It's a shortcut because it ends up taking less time. But what it really is a great organizational method for doing integration by parts where we might actually have to do multiple integration by parts. Like in the case of x squared e to the 3x, where we had to do integration by parts twice. In the case of x to the 4th sine x, we'd actually have to go out and do integration by parts 4 times, which could be really time consuming and could get very, very messy. So what we're going to do is we're going to take advantage of the fact that for each integration by parts, we end up with uv, 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 uv until we finally finish, right? And until we finally take our final integral. So what I'm going to do here is I'm going to establish, okay, I've got on one side of my table I will have u, and on the other side of my table I'm going to have my v's, okay? And so what I'll do is, just like as if I were doing my integration by parts, I'm going to select a u. So in this case, remember what we said, that we want a u to be our powers of x. So I've got x squared here. Okay, and then that will be then dv, or my first dv is going to be e to the 3x, and I'm just going to write that there. Eventually we're going to make them into v's, but not right now. Now what I'm going to do is I'm going to take the derivative. As I go down the u, I'm going to take the derivative. So I'm going to take d dx first, and so this is going to end up being 2x, and then I'll take the integral again, the derivative again, and that gives me 2. and then I'm going to finally take the derivative again until I get down to 0. So I got x squared, 2x, 2, and 0. So on my u's, I'm taking the derivative. Then on my v's, what I'm going to do is I'm going to take my integrals. So the integral of e to the 3x is 1/3 e to the 3x. And then I will take the integral again, and I get 1/9 e to the 3x. And I'm taking the integral of my previous term. And then I'm going to take the integral again, and I'm going to get 1/27 e to the 3x. So what this ends up giving me is it actually ends up giving me all of my UVs, all the values that I had before, okay? All I need to know now is that the signs are going to be switching. They'll switch off each and every time. So my integral, the integral of x squared e to the 3x, is going to be equal to, dx, excuse me, is equal to this first UV, so that's 1/3 x squared e to the 3x. Then we'll minus, okay, the next term, which is 2x times 1/9 e to the 3x. So this is, we'll go on a diagonal. And so that's 2/9 x e to the 3x. And then we'll add plus 2 times 1/27 e to the 3x. So 2/27 e to the 3x plus c. And that, in fact, gives me my integral. And you can see it takes a heck of a lot less time, and it's very, very organized. Very, very organized. Let's do it with x to the 4th sine x. And what you'll notice is that this one's going to save us a lot of time. Okay? So we go up, we've got the integral of x to the 4th sine x dx. I'm going to let u be my power of x, so that's x to the 4th. And I'm going to take my v, then, is going to be starting out at sine x dx, essentially. So on the u side, I'm going to take my derivatives. So I got 4x cubed, and then I have 3x squared, 4x cubed, 12x squared, okay, 24x, and then 24, and then finally 0. Then on my v side, I'm going to integrate. So the integral of sine x is negative cosine x, and then I will take the integral again. I'm going to get negative sine x, and then I'm going to get positive cosine x, and then I'm going to get positive sine x, and then I'm going to get negative cosine x again. Okay, notice I stop when I hit the 0, right? When I've zeroed out, and basically what that means is that there's nothing to multiply by any longer. So now I'll take the first set. I'm going to get the integral of x to the 4th sine x dx is going to equal negative x to the 4th cosine x minus 4x cubed sine x. But actually we need negative, so minus 4x cubed negative sine x, okay, then plus, okay, 12x squared cosine x minus 24x sine x plus negative 24 cosine x plus c. We go in and simplify now. We end up with negative x to the 4th cosine x plus 4x cubed sine x plus 12x squared cosine x minus 24x sine x minus 24 cosine x plus c. And what you'll see here, okay, a couple of things. One, just make sure when you're doing your tabular method that we do switch signs. So this starts out with a positive sign, okay, right? It just turns out it's negative because it's x to the 4th times negative cosine x, okay? Then we've got a minus, and then this is going to be minus a negative term, and that's how we end up with a positive term. Then plus, then minus, then plus again. Okay, and that's how we use the tabular method. It's actually really quick and really great, but only, so the tabular method only works, or it only really works, when one of the functions is a power of x, is a polynomial basically, excuse me, or a power of x in our case. Otherwise, we're going to have to utilize more traditional integration by parts. Okay, we're going to get an example of one where we're using natural log of x, with a power. And in that case, you actually may want to use the traditional integration by parts rather than using a tabular method because it might be a lot easier to simplify. So why don't we take a look at that one? Now let's look at some special cases. So these special cases, we're going to look at them because they should help you to kind of understand what are the different kinds of variety that we could see with integration by parts, and also to look at ones that are very common, right? That could show up a lot and that may not be immediately obvious as to how you might go about solving them. So let's take, for example, let's say what we want to do is we want to integrate x cubed ln of x dx. Okay? Now, you might look at that and say to yourself, you know what, I really want to use the tabular method right there. But I'm going to indicate to you that probably that's not the best route to go here. And the reason why is you kind of want to notice, okay, that d dx of the natural log of x, okay, is going to end up equaling 1 over x, right? And so what we'll see is that when we go in and we, in fact, utilize our integration by parts method, that's actually going to end up canceling out one of our functions or allowing us to combine our functions to make the second integral really easy to solve. So what we're going to do here, instead of using the tabular method, is we're actually going to use our traditional integration by parts, but we're going to make u equal to ln of x. Okay? And that's actually one of the tricks when we're dealing with natural log, especially if it's natural log times some polynomial. Is we'll let u equal natural log of x, and then du is going to equal 1 over x dx. And then our v here in this case is going to equal x cubed, and dv is going to equal x cubed dx, and then we'll end up with v is equal to 1/4 x to the 4th. So then what's going to happen when we put it into the formula is we're going to end up getting 1/4 x to the 4th ln of x minus, and this will then be the integral of 1/4 x to the 4th times 1 over x dx. Well, good news, right, is that 1 over x and the x to the 4th are going to combine. So this is going to end up giving me 1/4 x to the 4th ln of x minus 1/4 times the integral of x cubed dx, which is great. It's great news for us. And then that's going to then equal 1/4 x to the 4th ln of x minus 1/4 times 1/4 x to the 4th. So what we finally get, plus c, plus our constant, we'll get 1/4 x to the 4th ln of x minus 1/16 x to the 4th plus c. And that is our integral. And so what you can see by selecting the very carefully selected u, or u equals ln of x, what we end up with is we end up with something that's actually much easier to solve, even if we were to then use the tabular method, which would require us to take many different derivatives and also take a lot of different integrals. Okay, we'd end up the same thing, but we'd have a lot more simplification to do. Okay, so if you end up with something like this, one thing to remember, or any kind of function, is that the derivative of ln of x is actually 1 over x, and that can make things a lot easier to simplify. So here's another class of functions where sometimes what we can do is we can actually, by going in and utilizing integration by parts, we can find the integrals for functions that we couldn't find before. And so a great example of this is the integral of arctan of x dx. And one of the tricks that we're going to do is to note that this is actually equal to the integral of arctan of x times 1 dx. Okay? So we're first going to notice that, and the second part is that I actually do know the derivative of arctan x. Okay? So d dx of arctan of x is equal to 1 over 1 plus x squared. So the fact that I know the derivative of arctan of x actually allows me to use integration by parts here. So what I'm going to do is I'm going to say, okay, well, I'm going to let u equal arctan of x, and then dv is going to end up equaling 1 dx. Okay? Because taking the integral of 1 dx is really simple, right? It's just going to be x. And we already know the derivative of arctan of x. So this is kind of like one of those things, it's a trick that we learn inside of when we do work with integration inside of calculus. Well, I've got a technique where I don't need to know the integral, but I do need to know the derivative. do I actually know the derivative of this function? And if I do, well, then what I can do is I can actually utilize this technique in integration by parts. So now I've got u equals arctan x, and I got dv equals 1 dx. So du is going to then equal 1 over 1 plus x squared dx, and v is just going to equal x. So now, using our integration by parts equation, I get x arctan x minus the integral of x over 1 plus x squared dx. The cool part here is now I can use a u substitution. I'm going to let u equal 1 plus x squared. And then du is going to equal 2x dx. Pull over my 2 and I get 1/2 du is equal to x dx. So what I'm left with now is this thing here is going to equal x arctan of x minus the integral of minus 1/2 the integral of 1 over u du. Awesome, I know the integral of 1 over u du. This is going to be x arctan of x minus 1/2, and this will be the natural log of u, and we'll just substitute back in 1 plus x squared, the absolute value of 1 plus x squared plus c. And that is my integral. So in this case, what we do is we take advantage of the fact that we actually know the derivative of this function, okay? And then we use like a trick. We basically say, okay, you know what? It's going to be that function that I know the derivative of times 1, okay? So now I've got a function I can take the derivative of, and I have another one that I can take the integral of. Boom. I now can find the integral of the entire function using integration by parts. Let's take a look at one last class of functions. All right, ones that actually may end up being, they're a little bit trickier, a little bit harder, mostly because they require us to keep a track of a lot of different things going on. And then there is a particular trick to doing them that, in fact, isn't immediately obvious. Okay, so let's take a look at, let's say, for example, I have a function like this. I have a function e to the 3x sine 2x dx, and I want to take the integral of it. So I want to integrate that function. What I'm going to notice is that the integral, or excuse me, that we'll have an infinite number of derivatives for e to the 3x, right? So if you take d dx of e to the 3x, it's just going to be 3e to the 3x, okay? And then you'll end up with 9e to the 3x, and then you'll end up with 27e to the 3x. But that e to the 3x is never going away, right? It's never going to disappear like it did in the case, like the functions disappeared when we had like x squared terms, okay? So we're going to continue to have that 3e to the 3x. And then if we look at sine of 2x, we're looking also at something that has an infinite number of derivatives as well, or an infinite number of integrals. Either way you look at it, it's fine. So d dx of sine 2x is then going to equal 2 cosine of 2x. And then when I take the derivative again, what I'm going to get is I'm going to get the negative 4 sine 2x, right? Okay, so both of these have basically never-ending derivatives. And consequently, they basically have never-ending integrals as well. Well, that's a problem for us. The problem here is that if I think about integration by parts and using integration by parts here, what I'm going to do is I'm just going to cycle through, right, e to the 3x and cosine x or sine x terms forever, okay? I'm never going to actually get to a point where I can just go in and integrate, okay, and end, right, and be done, like I have in every other example that we've worked with thus far. So what I'm going to do is I'm going to do a little bit of a trick here, okay? It's some algebra that we integrate into our calculus, pardon the pun. So let's let I equal the integral of e to the 3x sine 2x dx. And what we're going to do is that we're then going to use our integration by parts. We'll let u, in this case, equal e to the 3x. And so du is going to equal 3e to the 3x. We'll let dv equal sine 2x dx. And so v is going to end up equaling negative 1/2 cosine of 2x. And if you have any issues with that, it's basically a u substitution. all right, where we substitute u equal to 2x. Okay? So now what I have is I'm going to have I is going to equal uv, so that'll be negative 1 half e to the 3x cosine 2x minus, and now I have the integral of v to u, so this is going to be minus 1 half times 3e to the 3x times cosine 2x dx. If I pull out all my coefficients, I end up with negative 1 half e to the 3x cosine 2x plus 3 halves integral e to the 3x cosine 2x. Well, I'm going to have to use my integration by parts again in order to do this integration right here. So I'm going to let u equal, and we'll use e to the 3x again, and we'll have du equal then 3e to the 3x. So dv is going to equal then cosine of 2x dx, and v will then equal sine, or 1 half sine of 2x. So what I now have is that this whole thing is going to equal negative 1 half e to the 3x cosine 2x plus 3 halves times the quantity, and it'll be uv, so it'll be times 1 half e to the 3x sine 2x minus the integral of, and this is v to u, it's 1 half times 3 e to the 3x sine 2x dx. And then I'm going to just do a little bit of simplification. That's going to equal negative 1 half e to the 3x cosine of 2x plus, and this is going to be now times 3 halves, 1 half e to the 3x sine 2x minus, and this will be now 3 halves, the integral of e to the 3x sine 2x dx. But here's the trick now, and this is actually something really interesting and kind of very, very clever. Notice that my integral, what I'm actually solving for, is e to the 3x sine 2x dx. And what I get here is I get the same thing. I get I get minus 3 halves, the integral of e to the 3x sine 2x dx. That's pretty great. Okay, what that means is that I'm going to end up getting something that I can, in fact, I'm going to make a substitution here and then just do some algebra. So what I'm going to do is I'm going to make that substitution. I'm going to set this value right here to I. So what I get now is I get I equals, and I'm going to do some simplification, negative 1 half e to the 3x cosine 2x plus 3/4 e to the 3x sine 2x minus, and this will be 9/4 I, because I in our original case was e to the 3x sine 2x. So now what I'm going to do is I'm going to do something that's actually really clever. I'm going to add 9/4i to both sides. All right, and just remember that I is it's what we're solving for. It's our integral. So what this gives me now is this is going to give me 13/4i is going to equal negative 1 half e to the 3x cosine 2x plus 3/4 e to the 3x sine 2x. And we'll eventually add a plus c in just a moment. Okay? But what we get now, and this is, like I said, this is pretty darn clever, is we're now going to multiply everything by 4/13. And remember, what we're trying to find is we're trying to find I. So I'm going to get I. So what I get now is I get, okay, when I multiply everything by 4/13, I get I equals, and this will be negative 2/13e to the 3x cosine 2x. And then this is going to be plus 3/13 e to the 3x sine of 2x. And then we'll finally add our plus c. So what we've done there is we've utilized integration by parts with these cyclical functions, right? These ones that have cyclical derivatives. all right, in order to get back to our original integral, and then we utilize just some basic algebra in order to go out and find out what that integral was. Okay, so what we do is we end up with, right, our original integral on the right hand side of the function, and then we add that value onto both sides. Then finally we could just take we multiply by the reciprocal, and it ends up giving me my integral. Okay, so this finishes up our mini lecture here on integration by parts. What you're going to see here is there's a big diversity of ways that we can implement integration by parts. And sometimes it's not going to be obvious that what we should do is use integration by parts, and that's where practice comes in. The fact of the matter is that when to use integration by parts, which u to choose, which v to choose, outside of like some of the simple rules of thumb that I put forward here, they're all really a matter of practice and finding out, and sometimes a little bit of trial and error where you kind of hit a dead end and you're like, okay, well, maybe I should pick a different u, or maybe I should pick a different dv. Okay, so what I suggest for you is you go in and you practice. This is the kind of thing you just got to go in, practice until it is second nature. Okay, and in addition to that, it will help you to just memorize how to do integration by parts. All right, this completes the lesson.